All right, so today, this title should say working with time series data. Apologies. All right, so today we're going to talk about time series data, and this is mainly about like how should you treat time series data. We'll see tomorrow that like with a lot of these time series models, you would have to do a lot of exploration of your data beforehand. So if you were going to do a time series project, if you're going to do a time series project for either the end of phase or for your capstone, EDA is actually extremely important because if you don't do EDA, you wouldn't know what to input into your models. So very, very important to take note of like some of these patterns that we're going to discuss with regards to time series data. So really quickly, what is time series data? As the name suggests, it is a series of values of quantity obtained at successive times, often with equal intervals between them. So the main thing is that your data is going to probably be ordered by time. So some examples, temperature of July recorded daily, so all the Julys and the daily temperature. Also another example, I would say actually this is probably one of the more common applications of time series in any sort of like forecasting data. And so either in like finance or real estate, anything that has to do with forecasting is very likely going to be time series related. So this example, the average weekly price of a stock in the past year, or just the average annual government budget in the past 30 years. Our focus for today and tomorrow is going to be on univariate time series that records a single observation or variable at different but equal time intervals. In contrast to univariate time series, there's multivariate time series where you can actually predict multiple things at once. But we actually don't get into this in this course. However, when we talk about time series with neural networks, which we'll get to at the end of next week, there is a potential application of multivariate time series, but most students actually don't get into that until after the course because it is quite hard to implement. All right, so now that we know a little bit about time series data, what are some characteristics of time series data? What are some of the things that you have to look out for before you even start modeling your data? So the main data trends that we're going to look out for, there are two, trends and seasonality. So with trends, you know, is basically what you observe. Is there like an upward, downward, flat trend? And seasonality is basically patterns. It's patterns that occur as a function of specific seasons. Are the variations quarterly, hourly, weekly? These are usually characterized by like repeating patterns in a line graph or in a scatter plot, depending on how you plot your data. And these, what's that called? The time frame of your seasonality is something that you also have to take note of. So an important pattern in time series that occurs is stationarity, which is an assumption that lays the foundations for time series forecasting and modeling. So stationarity is something that you have to look out for in your data. And if your data is not stationary, we're going to go through some things that you can do to make it as stationary as possible. Before we get into it, any questions so far? All right, I will say a lot of the lessons in this topic, they're actually pretty simple to grasp. It's just different ways that you can deal with time series data, different ways to visualize and treat time series data. And I would say it's just learning all these new methods, such as like learning new methods in pandas. All right, so stationary data, which is what we want our data to look like. Stationary data is data in which your summary statistics, the mean and variance, are not a function of time. So that means over time, you want your mean to be fairly constant. And if it's not, we'll talk about later how we can make it constant. But basically, over time, you want your average data to be fairly flat. So if you're collecting stock prices, a stationary stock price is probably something that's more stable, that hasn't really grown or gone lower over the course of time. So if you have a stock price that is like pretty similar now as it was maybe 10 years ago, you could assume that it's fairly stationary just because of its constant mean. not just constant mean, but you also kind of want to look for constant variance. I will say this is a little harder to control for, but constant variance is preferred. So constant variance, and we talked about this homoscedasticity, if you remember our terminology from phase 2. Something, another part of a series being stationary is that it also has constant variance. So let's say that, I don't know, something that measures variance in finance is volatility. If you see like something is fairly, let's say there's like the stock price of Bitcoin when it first came out. The movement of Bitcoin was fairly small when it first started, and then only in like recent years you see like huge jumps up and down. That is not a constant variance, right? Because the amount that the price of Bitcoin moved, I don't know when it started, but earlier on when it was worth like dollars, didn't fluctuate as much as it does now, where it fluctuates like apparently tens of thousands of dollars. So that's also something that is a preferred pattern in your data if you want your time series models to work well. Covariance, same, similar thing here. Questions so far? All right. So why does data have to be stationary for modeling? Well, stationarity is important because without it, the model describing the data will vary in accuracy at different time points. So this is very similar to when we were talking about why is homoscedasticity important for linear regression, right? So if you had a homoscedasticity plot that looked like, and let's just draw a really quick example. Let's say this is your error graph. I remember there's like a red line that goes across the middle. And if your data points sort of look like this, sorry, your residuals sort of look like this, that's basically what this is saying. Model describing the data will vary in accuracy at different time points. In this example of like a linear regression model, and let's assume this is like housing prices or something. As prices of houses get greater, your variability in your predictions gets greater as well. So what this means is it sort of loses predictive power as housing prices get higher. You can say similarly, if I were to build a model to predict the price of Bitcoin, you can imagine probably predicts with less error at the beginning of Bitcoin. Right now, probably lots of error if I was using one of these models. Questions about that? So this is kind of like the importance of stationarity. Stationarity also lays the foundations of the typical time series models, and we're going to talk about these tomorrow. So AR, MA, ARMA models. So a violation of stationarity can cause problems in prediction, and very, very similar concept to what I was talking about here. Having stationary data basically allows for consistency in your predictions. All right, so several ways to test for stationarity. First, you can visually examine the data. Sometimes if you have a robust enough data set, or if your data is across, if you have enough data points on whatever it is you're trying to find. Oh no, hold on, let's see what's wrong here. Sorry guys. Let's pull this out over here. Should work. There we go. All right. So sometimes just by looking at data, you can determine whether there is stationary or not. Like for example, here it's pretty obvious that it is violating the mean part of stationarity, right? Like the average is obviously changing over time. This is the sales of shampoo over a 3-year period, and each data point is 1 month. So you can see like over 3 years, the average price of shampoo has actually been increasing over time, so it violates that part of stationarity. In terms of variance, a little harder to see, but there are some statistics that can help us determine whether something is stationary. Questions so far? All right, so we can also examine our summary statistics. So just by printing, what is this? All right, let's just use shampoo here. Go. Okay, so just by using summary statistics, Let me just zoom in real quick. You can see that here there's a mean. What I'm doing here is I'm splitting my data into two. And here you can see that if we were to look at the front half of our data, it has a mean of about 200. If we look at this latter half of our data, it has a mean about 421. So based on that, obviously that you're violating that average assumption. And then also, if we're looking at variance across the two parts, you can see that the variance at the start is much lower. It's about 3,300, whereas towards the end, you get a greater variance of 17,000. So it also is violating your variance, your constant variance assumption. This I will say is more on a simple level if you just want to see, whether at two different parts of your data you're seeing different patterns. But to do it more scientifically, there is a stationarity test that is a statistical test that you can use to just quickly determine whether your data is stationary or not. So that test is the Dickey-Fuller test. And it is a statistical test. So it does the same, you use the same procedures as we did back in phase 2. You have your hypotheses set up. So for the Dickey-Fuller test, the null hypothesis is that your time series data is not stationary. So if the test statistic is lower than your critical value, you will reject the null hypothesis and say that your series is stationary. So for stationary data, you would want a low p-value if you were to use the Dickey-Fuller test. I don't have the example here, but there is the worked example in one of the lessons for sure. And the Dickey-Fuller test is actually in the stats models module. Questions so far? All right. So the idea is we want our data to be stationary. So there are some steps that can be taken to stationarize your data. So the idea here is you want to remove any trends, and you also want to remove any seasonality. We do this by taking differences of the variable over time, log transforming, or seasonal differencing. And then we're going to go through some of these real quick. So before we get into differencing, which is one of our most, I would say, one of the most important things for getting rid of overall trends, we have to talk about lag. So lag, if it's not apparent, for some specific point t, the observed t minus 1 data point is called the ith lag of x. So the 1 period lag of today is yesterday. The 3 period lag of today is 3 days ago. Anything to clarify about that? All right, and the way that we use lag to help get rid of, to help achieve stationarity is through differencing. So differencing basically removes your data's dependence on time. And it's really just performed by subtracting the previous observation from the current observation. And we'll see with some graphs later that if you have like a trend that's constantly going upwards, you end up with a flatter overall data set. So all you're doing is the new difference is just your current observation minus your last observation. So if we have a time series data set going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is just a really simple example, and we want to difference it by doing a lag of 1, what would the result be? So if we have this data set of 1 through 10, and we difference all of it, we actually will end up with a straight line because we're just going to take each number and subtract the number that came right before it. And because, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you're incrementing by 1 each time. If you difference this data set, you just get a flat line at 1. So you see how you can get from a line that's going upwards from 1 to 10 to just a straight line at 1. Questions about this? All right, so just based on this example where you're taking like a diagonal line and flattening it, that's what we want to do to any data that has like overall movement trends. This is the manual code. I also will show you later here, there is a built-in function, but just wanted to show that with this manual function, it's actually pretty straightforward. We have a data set of data points, and this can be our lag interval. all we do is take the individual data point and again, subtract it by however much lag data point you want. So let's just take a look at what our pre-lag data set looks like. And we can use our difference data, which I'm surprised we actually don't have here yet. Oops. So our difference data will look like this. If we difference our shampoo data set, oops. What happened here? Sorry, guys. We'll just use this function for now. But this differencing method will basically do the differencing for you. And by default, it is 1. So we run this real quick. You can take a look and see, well, the first observation is actually going to be nothing because you can't subtract anything from the first data point. But from that, you can see that with our same data set, our same shampoo data set, which was up here, when we difference it, the curve actually flattens overall. So there is no like upward trend. Questions about this so far?
Excuse me.
Maybe I'll check. Oh, sorry.
Okay, go ahead.
Would you be able to explain like why you're flattening it exactly?
Yeah. So I don't know if this explanation will help you, and if it doesn't, let me know. I like to think of why differencing flattens it in a similar way as to like taking the derivative of a function. So if you had like a function like y equals to 2x, right? And that's like a diagonal line with like a gradient of 2 or a slope of 2. In a similar way, differencing kind of works something like that because you're looking at the incremental change over time. And if you have something that's incrementally increasing and you take the difference of that, you flatten the line. So like how you take y equals to 2x, and if you were to differentiate that, you actually end up with a flat line at 2. So it's kind of similar in that way. I don't know if that.
Is it like taking the acceleration?
Yeah, kind of like, yeah, that's right. It's kind of like looking at the rate of change of the curve. Yeah. Not exactly that, but oh, sorry, say that again.
Why would you want to get something similar to the acceleration? Like, how does that help you from modeling? That's my question, I guess.
So why that is good for modeling, we'll see tomorrow that it's actually one of the inputs of your model. Basically, for your model to be able to predict, to forecast future time points, it's easier for the model to forecast future time points if there is no overall trend. Or if you tell your model, what is this overall trend to begin with, it can flatten it. And imagine it's easier to make predictions on something that is flat versus something that is like always increasing at some variable rate. That makes sense?
Yeah.
All right, Ali, you're about to ask something as well.
Yeah, I want to ask a question about, we have to do all of these things for every feature in our data set?
Oh, that's a good question that I actually didn't really address. For time series, let's say you have like stock prices, right? You have stock prices and you're trying to predict the stock price of the S&P 500 tomorrow. With that, your data set would only have your stock price. So this is just one variable. We're only dealing with one variable. And because it's one variable, you're technically doing it for every variable, but yeah, you will only need to do this analysis for whatever the variable is you're trying to predict future movements of. Tomorrow we'll talk about as well how you can incorporate other things. So if you wanted to predict the price of the S&P 500, how you might incorporate like the price of, I don't know, US Treasuries bonds, is that a thing? Or I don't know, the price of gold, for example. Tomorrow I'll talk about how you can incorporate that as well. But this is just using past data to predict future data on like one feature.
And is it working accurately? For example, for recommendation system, we considered latent features, and for this one, just only one variable? It works?
Yeah, it works to some degree, which is why it's being used. I have like a whole piece of commentary on like the usefulness of traditional time series algorithms that I feel like I will go over probably after this today, if we have some time, which actually, yeah, I might talk about that at the very end, but it would, yeah, I'll probably talk about that at the very end, just to like quickly introduce some of the models before we get into them tomorrow. And I'll talk about like some of the possible applications of these models, how well they do in practice, and what are some other things that you can try on top of these models. Yeah, let me
Thank
make
you.
a note for myself to like address that. Any other questions? Okay. All right. So yeah, basically for our models to work better, you want to determine how do I get my data from like some trend to becoming flat. Sometimes we have to difference the difference data. So you might actually want to difference your data 2 times to achieve stationary data. This is more, and why I made the comparison between this and taking the differential of a function is because if you are familiar with like, taking the differential of different functions, differencing your data this way also is kind of like connected in that way. So if you have a piece of data that, let's say the overall trend, if you were to plot like an average line throughout, let's say the overall trend was a straight line. Like for example, with this shampoo data, we saw that, all right, you can sort of fit some sort of straight line that like, that demonstrates like an overall trend. If you see that, all right, you can maybe plot a straight line through my data, you probably only need to difference it once. However, if something is more of this kind of shape, and those who are familiar with like calculus a little bit more, this is more like a quadratic curve, then you would want to difference your data another time and you could achieve even more stationarity. So just something to keep in mind, not super important to like internalize this, but if you're familiar with calculus, this will give you like an intuition on how much you want to difference your data. I don't know if anyone wants to clarify anything about this. All right. So differencing, you can also potentially difference your data multiple times to get it to be as stationary as possible. So after stationarity, the next thing we want to address is autocorrelation that remains in a different series. So time series data usually exhibits 2 kinds of behaviors. So often you can predict the value in time series by using a past value or values. Other times the past values could be misleading. So in the example of a stock market, every day you have, every day your stock prices will experience some shock due to randomness, right? And it's hard to say, all right, are there any like seasonal trends? Are there any like overall movement trends? And the effect of that shock will generally diminish quickly and will have little effect on future prices. And so with these shocks, you, in some way, you don't really want to incorporate that into your model. You know what I mean? Like if you have like, for example, I don't know, one day you have, I don't know, Elon Musk says something, right? And the price of Tesla just shoots up for no reason and goes right back down. You want to kind of ignore that shock. And so determining which behaviors are present in our time series consistently is essential so that we can properly model that behavior. So that's also why like an ED analysis for this is really, really important. And the more contextual information that you have on your data, the more informed your decisions can be.
I just had a question.
Mm-hmm.
When I look, for example, at like a stock market trend, let's say for a month, so like for like, let's say for Tesla or whatever, when it shows me like by each day, like if it shows me like 30 points, let's say, is it showing me based on like this concept only like which, is it choosing based on this concept like the specific time of day to show for that, to like for each day, meaning does it choose like there's a lot of points in the day it could have chosen?
Yeah.
So like does it choose like on this, based on this concept, that point in the day that like that's not fluctuating randomly?
So I know that specifically with stock prices, and I'm no expert, this is like based on like other projects that other students have done. But I know that for stock prices, the way that you can the data that you can use, you can actually get like, you know how like the stock market opens and closes every day? You can actually just get like the closing price every day or the opening price every day, or you can also get like the daily highs and lows. So based on like what your data source is, I believe they should tell you like which point of the day
Right.
your stock price is. I think you can also get like a daily average price. But yeah, there are some pretty like
fluctuation.
Yeah, exactly. But if you do have like a spike that lasts like just 1 week and goes away, that is something that you would have to remember as part of your data.
Okay.
Anything else? All right, so let's talk about autocorrelation. Autocorrelation, as the name suggests, it means like there's some correlation happening. And autocorrelation is the correlation between one time series and itself shifted by a number of periods. So let's say you have, you know, like an arc shaped pattern one day, but then maybe a week later, you have the same arc shaped pattern. Those two time periods, if you were to overlap them over each other, they would be correlated. And so something to also look out for is autocorrelation. And we'll sort of see in a couple plots later, or autocorrelation usually happens in the next 1 or 2 lags. So let's take a look at our shift in our shampoo sales. And let's plot this real quick. So these are graphs of our shampoo sales shifted by a day. This is by 1 day. This is by 2 days. Now we would say that they are autocorrelated with each other if after there is a shift, the lines still overlap pretty well. I would say this is not super autocorrelated, but you literally will take like the correlation coefficient between these two pieces of data with it shifted. Questions about like the concept of autocorrelation. So autocorrelation is basically a data set's correlation with itself, like shifted some number of time periods. There is an easier way to test for autocorrelation versus just looking at it on a graph. And that's using ACF or PACF curves. Very neat. It's actually built in within stats models. And what the ACF plot looks like is something like this. And so what this is doing is it's showing for each lag, for each like shift in time, literally what is the correlation coefficient between two sets of data. So you can sort of see here, like shifted with 0, of course you have a 1, you have a perfect correlation there with itself. But if you're shifting it 1 day, if we take the correlation coefficient between these two lines, it is still about like 0.7. And then here, shifted 2, the correlation actually does go up to like 0.75. And autocorrelation is something that you want to take note of to be used in your time series models that we'll talk about tomorrow. So questions on like reading this graph.
What units are the x-axis in? Yeah.
The x-axis should be an integer. So this is literally just like 1 lag, 2 lags, 3 lags, 4 lags, 5 lags. So it should be just like the number of time unit shifts. And again, that will determine on your data set. For in this case, it would be like months. That's because the shampoo sales data set comes in months. Anything else? Yeah. So yeah, these are literally the correlation coefficient from like 1 to -1. And the idea is you want to remember which points have like high autocorrelation. So for example, here, I would maybe remember 2 as like where your data set is correlated with itself.
Can you explain one more time what it means to be correlated with itself?
Yeah, so I think a better example would be to do something like this. So let's do a pd.data frame of shampoo. Okay, I think I got to do it like this. And then shampoo sales lag 1. And let's transpose that. Never mind, that didn't happen how I thought it would. Let me do this real quick. So shampoo looks like this. And then shampoo sales, lag 1. Looks like this. Probably want to do like a p.concat here. I forget if I need the axis. There we go. So basically we take the original shampoo sales, take shampoo sales shifted by 1 time block, and basically they're saying that these two are correlated with each other, and that would be autocorrelation. So as long as you have like a fairly high correlation between this, it can be your lag 1, and here I have like the lag of 2. Looking like this, let me make this a little smaller. Looking like 2. So they would literally just take the correlation coefficient between these two, and that would be like, for example, this is itself with a lag of 2. If we go down to here, we can see that this has an autocorrelation of about 0.74, 0.75. And if you have like a high number here, autocorrelation is present, and you'll want to take note of it for your modeling. Is that helpful?
Yeah, thank you.
Awesome. Anything else about autocorrelation?
So autocorrelation is just trying to help us determine how far to lag or how far to differentiate.
Yeah, I would say it's hard to explain now before you get into the models, but it will help you determine that, like, let's say you have a high autocorrelation between now, let's say there's a high autocorrelation between like your time series data and the time series data 2 with a lag of 2. Well, that's saying that if you want to predict 2 days from now, today's price might be very useful in determining the price 2 days from now. Does that make sense?
Yeah, that makes a little
Yeah.
sense.
Yeah, I think it would be, yeah, I think what I mentioned that I was going to talk about after that, I'll talk about basically, yeah, I'll talk about like what kind of models we're about to see and why this information is important.
Okay, thank you, Ian.
You're welcome. Anything else?
Yeah, is there a standard number at which you would consider it autocorrelated, like over 0.6 or etc.?
Yeah, that's a good question. Not typically, because usually when, and again, we'll see it when we get to the models, you just have to give it one value in which it has high autocorrelation. So in this case, I would remember that, all right, with a time shift of 2 is where I have the highest autocorrelation. I would do that relative to the other numbers, if that makes sense. Like, I'm just saying, all right, out of this, I would maybe take note that, yeah, there is quite a lot of autocorrelation happening, like with the first maybe 3 time steps. But again, there's not really a threshold to look out for. This is also something that you can tune in your model. If you say like, all right, let's say there is some, like both 1 and 2 time lags are pretty autocorrelated with each other, that could also be something that you tune in your model. And again, we'll see how that comes into play with your model tomorrow. Anything else? All right. Now, other than autocorrelation, something else that I would say you would use in conjunction with this ACF plot is a partial autocorrelation plot. Oh yeah, so yeah, looks like the first 4 lags, before I move on, the first 4 lags have pretty strong autocorrelation. Note that for future model building. And then sometimes autocorrelation will propagate down to other lags, which is kind of this relationship that we're seeing here. So sometimes we see a shape that looks like this, where over time it gets less and less correlated. I will say another common pattern that you might notice is you have, let's say this is always at 1 because it's always correlated with itself. You see something fairly high here, after which everything just dips down. So that's another common pattern that you might notice. just in case you see that and you're like, why? All right, so yeah, the influence of a strong autocorrelation will cause additional lags to be highly autocorrelated. So this, if you have strong autocorrelation, your additional lags are likely also going to see high correlation with each other. And something to mitigate that, because the autocorrelation sort of like carries on the more with a few lags. To discover the true relationship between the lags, we use PACF, partial autocorrelation. So PACF looks at the correlation between a point and a particular lag without the influence of intermediary lags. And this will help us see the direct relationship between lags. So if we were to plot this PACF, you can see something similar to the pattern where I was talking about, where after a certain point, it really does dip. Usually you want to plot both of these. And from this, you'll see that you start off with around, I think, yeah, this number is the same as we had before with one lag. But afterwards, all of these later lags, they try and discount the prior autocorrelation, if that makes sense.
Sorry, I have a question. You said that autocorrelation, if you have a lag of 2, an autocorrelation, that basically means if you're predicting price, that in 2 lags from now, you would have a good chance at predicting price.
Yeah.
Why do you want to mitigate if it means it's more predictions?
We don't want to mitigate. We're not using autocorrelation to mitigate, but we're using the patterns of autocorrelation to we're not trying to get rid of autocorrelation. If that's what you're asking. You're trying to use autocorrelation to determine what would be useful in making predictions.
But then you're trying to remove the role of the intermediary lags.
Okay. Yeah, I get what you mean now. So let's say we were looking at like the second lag and that autocorrelation. There is a chance that this autocorrelation is only high because of the one lag autocorrelation, if that makes sense. Just due to like, the incremental nature of data, that could be an issue. So this number is 0.75. It could be because of, this number also being fairly high. So you see how in this plot, the partial autocorrelation plot, the number for the second lag goes down because we are calculating this autocorrelation between 2 lags and no lag while also discounting the one lag.
Sure. Okay, that makes sense. You're finding like the independent predictive power and getting rid of the influence of the lag before it.
Yeah, that's right.
Okay, thank you.
Which is something that you, again, want to take note of for when you're modeling. Any other questions so far? All right, well, this is the end of this notebook, but I think with like the time remaining, I can talk a little bit about what to expect with the models and why this is so important. So the set of models that we're going to talk about tomorrow, which include like AR models, MA models, ARMA, ARIMA, Ceramax. I think there might be one more, but I forget. These are actually all linear models. And you've seen that I've drawn some similarities between this and linear regression. That's because all the models we're going to talk about tomorrow are linear models. And the reason why like you have to find, all right, which one has high autocorrelation here is basically what we will do in those models. Just using this as an example, we sort of see here, all right, the one lag time is pretty correlated with our current lag time. And so we're saying that, all right, if I want to predict tomorrow's price, today's price is pretty important. And what we're going to do with our models, this is actually going to be a feature, if that makes sense. So basically, as part of our model, our price today is going to be some coefficient multiplied by the price yesterday, the price of like the one lag time. And that's pretty much how these time series models are built. With autocorrelation, you will really just use like your lag time as features. And in the case of differencing and if there are overall trends, that is also incorporated into your linear model. So for example, with the differencing, you'll actually find out, and you see that with the differencing gives you an overall like change in basically like the incremental change in your data. And so you will also incorporate that into your model. So you could say that, all right, one feature in my linear model would be some coefficient multiplied by the change in your data from yesterday to today for tomorrow's price. But the fact is, I think what I want to drive home is that all of these models that we will be talking about tomorrow are in the end linear models, which is why this information that you find out during your EDA of your time series data is important. Questions about that? Now, the fact that there are linear models should send off some like sirens or red flags, maybe not red flags, because like you saw that in your phase 2 projects, there are kind of a lot of issues with linear models, right? There are a lot of assumptions that you have to fulfill. Your data inherently will not, be linear. Like you're saying, if I can linearly predict the price of real estate using the prices of real estates like last year and 2 years ago, does that make sense, right? Because time is just so, I don't know, random. And so with that, the argument comes with like, why are we using these traditional models then? So these traditional models, these linear models, they have performed okay. They have not performed like really poorly. With more features and the more granular you get, like for example, maybe you can say like the price tomorrow is going to be like 1/3 the price of today, plus like, I don't know, 0.5 the price of it was yesterday, things like that. The more granular you get, the more what's the word, intricate your predictions can be. There have been a bunch of other models that have come out post these traditional models. For example, if you were to look into your appendix, Facebook actually created a model that is, it's called Facebook Profit. And it is something that anyone can use. It's a package that you download and use. They actually introduce some like learning techniques from your data. Additionally, and we'll get to that in neural networks, you can actually build neural network time series models. If you're curious as to like which specific kind of neural networks, it would be LSTMs, long short-term memory models. And basically those models will learn intricate patterns from your, about your data to make predictions rather than just using linear relationships. Now, the trade-off between these two sets of models, like these traditional models versus the more advanced like neural network models, is even though you end up with much better predictions with neural networks, you lose a whole level of interpretability. We'll talk about this when we get to neural networks, but neural networks are black box models where you feed in inputs and the outputs are like, all right, these are our predictions. Most of the time they predict quite well, but you have no idea why that is the case. And this brings us back into like, and I do want you all to like start thinking critically about why are you creating these models? Models are created for prediction, yes, but they're also created a lot of times for inference, right? If you want to figure out like what are the factors that affect the price of a house, or what are the factors that will affect your classification of a person churning versus not churning, models are also built for inference, and you can learn a lot from your data based on your model's outputs. And so with black box models, you can't do any interpreting, or you can, but it's a lot harder to do that. And so why are some industries still using traditional like linear models? It's really for interpretability. And if you want to definitively say like, all right, a change in this feature is going to lead to this much change in this feature, or give it a higher probability of being classified as like 1 or 0, you want that interpretability still there. So something to consider. Complexity, higher complexity is not always good, because it's harder to learn from something that is highly complex. Because I know that there is a whole like subset of people who are like, why should I learn these traditional time series models when there are better alternatives that will predict with much higher accuracy? So do keep that in mind. I will talk about like those, I will also be talking about those more advanced time series models when we get there, but I do think that these are important. If you are very keen in finance or real estate, I've seen that like in interviews, they do ask about these more traditional linear time series models. So keep that in mind. All right. Any other questions to wrap up?
Excuse me, we are predicting, for example, price or temperature based on the previous results of them, right?
Yeah, that's right.
For example, if today is 75 in Florida, next year, January 12 would be 75.
Yeah, exactly. That is like,
this is what we are doing in traditional case.
Yeah,
okay.
That's right. There are a couple models that we'll speak about tomorrow that you can also include other variables in making the prediction, just like you would with a linear regression model. So we'll talk about that tomorrow too.
Okay, cool. Thanks.
You're welcome. Anything else? All right, then. I'm going to send out a bunch of resources about time series data for you all to read if you're interested in taking a deep dive into this. But yeah, as usual, any questions, just send them my way. If not, I will see you all tomorrow because we'll finally talk about the time series models then. But yeah, I'll see you all at your one-on-ones, if not tomorrow. All right, have a good rest of your day, everybody. Bye.